Welcome to the first lesson in our sixth module in Physics 1, Work and Energy. So this unit is mainly going to be devoted to the very important topic of energy and the closely related concept of work, which is what we're going to be starting with in the first lesson. These two quantities are scalars, and so they have no direction associated with them, which often makes them easier to work with than vector quantities such as acceleration and force. So today we're just going to be talking about the work done by a constant force to keep things pretty simple and introduce the relationship that represents work. So work done on an object by a constant force, constant in both magnitude and direction that is defined to be the product of the magnitude of the displacement times the component of the force that is parallel to the displacement. And I have an image here that's going to help you see what I mean. So we have some object here in the box, and it is going to be moving some distance d, which we're going to call the displacement, and it is moving that way because there is some force being applied to it. Now, the way that we're going to calculate exactly how much work is done is we're going to have to find the component of force that is perfectly parallel to the displacement. And typically that's going to mean doing a little bit of right triangle trigonometry. Now, if the force is already parallel to the displacement, then we can just take the product of the force and the displacement. But if the force is at some angle theta to the displacement, then all we have to do is take the product of force and displacement and multiply it by the cosine of that angle theta. And that should make pretty quick sense if you imagine this triangle that I have drawn here for you on the screen, and we're taking this angle theta. The component that is parallel is the side of this right triangle that is adjacent to our angle theta. So that's going to be cosine, because when you think of SOHCAHTOA, CAH cosine theta is equal to adjacent over the hypotenuse. All right, so this adjacent side we'll get from taking the cosine of theta. All right, so in this case, we would say that F cosine theta is the component of the applied force that is parallel to the displacement of the box. Alrighty? So let's look a little closer at work is equal to FD to deduce what kind of units we're dealing with. The SI unit for force is newtons, which we usually use a capital N to denote. And the SI unit for displacement is meters, okay, which we usually use a lowercase m. So work has units newtons times meters, which we're going to call moving forward as joules, typically denoted with a capital J. So for future reference, two common non-SI units for work are the foot-pound and the erg. And you'll see the equivalences for those there on the screen, so you might want to take note of that for future conversions. Obviously, since work is equal to the product of force and displacement, if a force does not cause a system to move, in other words, if there's no displacement, no work was done on that system. So it is possible to apply large amounts of force to a system, yet do no work. You need both force and displacement to do work. Likewise, just because a system is moving does not mean that work is being applied to that system. Recall that force is actually equal to mass times acceleration, meaning that it is a product of acceleration, and you can only have acceleration when you have some change in velocity over time. Therefore, work is really just a product of acceleration, just as force is. So if there is no acceleration, then there is no work, because if there's no acceleration, then there is no force. So let me restate one more time. Just because an object is moving, that doesn't mean work is being applied to it. For instance, if an object is moving with constant velocity, then no forces are being applied to it, causing an acceleration, and therefore no work has been done. Run that back a couple times if you need a second to really let that sink in. Also, keep in mind that if you're measuring work done on a system in one direction, then any forces applied to the system that are perpendicular to the displacement are not doing work on the system. Because if work is indeed equal to the product of force and displacement times cosine theta, then you need to recall that cosine of a 90-degree angle is equal to 0. So then you're just multiplying the product of your force and displacement by 0. Therefore, we will have 0 joules of work if you're applying some force that is perpendicular to the displacement. Now, when we deal with work, as with force, it is necessary to specify whether you're talking about work done by a specific object or done on a specific object. It is also important to specify whether the work done is due to one particular force or if work is done by some total net force, in which case we would want that capital sigma for F. So we have to take the sum of all the forces and then multiply that sum by displacement. It would look something like this. Work is equal to the sum of our forces multiplied by lowercase d, which is displacement. So let's calculate the work done on the crate in this image here. All right, let's take a look at what's going on. So this is the crate we're discussing. It's going to move some displacement to the right equal to 40 meters. All right. There is some applied force at an angle theta of 37 degrees. All right. There is a normal force that is equal and opposite to the force due to gravity here. And because of that normal force and the fact that we're not neglecting friction, then there is a friction force that is what we would say opposite to the displacement. Okay. Now, so what is given? What's given is that the crate is 50 kilograms. Okay. I'm giving this to you now. If the crate is 50 kilograms and the displacement is 40 meters, I can give you now then that the applied force is 100 newtons, and then the resultant friction force from the normal force is 50 newtons. So it seems trivial for this problem since we're dealing with a flat surface, but you have to decide what your coordinate system looks like. So in the image, I've already given you a regular XY coordinate system. It's like the normal default XY plane, which will definitely be the best option for this setup, simply because the displacement is pointing in the positive X direction. Now, 4 forces are acting on this crate, okay? But 2 of them are in perfect balance at 90-degree angles to the displacement. That's the normal force and the force due to gravity, which you see here. So they do not contribute to the net force or the work done on the crate. One force, friction, is parallel to our displacement, but has the opposite direction. So we say it has an angle of 180 degrees to the direction of the crate's displacement. That's going to be a full 180 degrees, causing it to point in the opposite direction. Lastly, our applied force Fp has a component that is parallel to the crate's displacement, which, as we discussed before, can be found using the scalar multiple Fp times cosine 37 degrees, since that is the angle with which the applied force is applied with respect to the displacement. That said, the net force F that is parallel to the crate's displacement would then just be Fp, or the applied force, times cosine 30, times cosine 37, because that is the component that is parallel to the displacement, plus the force of friction times cosine 180 degrees. All right, because if we're considering the positive x-axis, the force of friction is at a 180 degree angle to that displacement. So we're going to go ahead and take the sum of these 2 forces, and if you plop those into the calculator, you'll have 100 newtons times cosine 37 degrees plus 50 newtons times cosine 180 degrees, and this will give you roughly 80 newtons minus 50 newtons, okay? Cosine 180 is just -1, so what's going to effectively happen is that we are taking negative 50 newtons. That sums to be 30 newtons, a sum of 30 newtons that is parallel and going in the same direction as our displacement. So that is the force in newtons that we are going to apply into our work formula, which, if you remember, is just work is equal to force times displacement. And then we're going to multiply that by our 40-meter displacement, giving us, in this case, since we've already rounded, giving us exactly 1,200 joules. All right. So we have a few practice problems here and a few qualitative practice problems here, conceptual problems, if you will. Go ahead and take a second to think about these problems on your own. This PDF is linked below. There is already a solution video posted for each of these problems. Have a look at that if you get in trouble. All right, I'll see you guys in the next one. Happy studying.